Hey guys, welcome back. Today we're going to be talking about the atomic nature of matter. This is a really cool subject, but it's also critical to understand all of the wonderful phenomena that we're going to be talking about from this point forward in the class. So, be prepared, have maybe a notepad out. There might be some interesting little notes you want to take. Not a whole lot of equations, but interesting phenomena that you want to be able to keep track of as we go forward. So anyways, right here on the title page, let's see if I can get my cursor up. Here we go. The atomic nature of matter. We see two photographs, and essentially what this is a particle that has been actually destroyed in a collider, and those parts are spinning all over the place. And it's in this way that we actually not only know that there are subatomic particles that fly through space from time to time, but it also gives us some idea of what atoms are made out of, the atomic nature. Atom meaning the smallest part. This over here is actually the inner workings of a nuclear reactor. Notice how it makes the water, it's actually in a pool of water while the reaction is going, and it makes the water glow blue. It's fantastically interesting. So these two things, it turns out, are very linked, because what are we doing in the nuclear reactor? Well, we're breaking atoms up, and we're releasing a lot of really cool subatomic particles. So Richard Feynman, who is one of the preeminent lecturers on astrophysics and physics in the 20th century, had this really great quote. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. And that is the nature of the atom. As we go through this, you'll understand by the end why they behave the way that they do. But when he was doing a lot of his writing, it was fantastically interesting that these atoms had the ability to hold on to each other when the right distance away, but if you got them too close together, they separated. We will be discussing exactly why that happens as we go forward. Here's a picture of Dr. Feynman down here. So the atomic hypothesis goes way back, actually. First off, here's a manuscript. This is actually out of I believe this is actually out of a Jewish manuscript translated into Latin, and dealing with what would eventually become the competing hypothesis against the atomic hypothesis. So the ideas about matter that existed kind of at the beginning of prolific writing and the printing press and things like that are important to keep in mind. Thought by Aristotle to be a combination of four elements, which is, say, earth, air, fire, and water. Today we would think of those as opposed to being the components of matter, because we now know that they're made out of atoms. But as opposed to thinking of them as the fundamental parts, probably Aristotle should be thought of as the first one to come about, saying these are the stages or the phases of matter, right? Earth being solid, air being a gas, fire being energy, or you could even say plasma, and water, of course, being a liquid. All right, so it was thought to be composed of atoms by other Greeks from the 5th century BC. And so Democritus knew Aristotle. These guys knew of each other. Socrates, who was Aristotle's kind of graduate advisor, is how we would look at it today, basically his teacher, did not like Democritus very much. They personally did not like each other one bit. Here's Democritus's bust down here. And it was proposed by him that there had to be some upper limit to how small you could make things before they no longer behave the way that they are. For example, if you were to take a tree, you can only cut a tree down so far before it becomes a branch. And when it's a branch, it's no longer a tree. And this is what he was arguing, is that the fundamental unit was so small that you just couldn't see it with the naked eye, but that didn't mean it wasn't there. We now know that Democritus was actually onto something. Aristotle, of course, said, I don't have any evidence for it, so I can't take that hypothesis. Let's go back to this picture over here, just to kind of verify what we're seeing here. Ignis is Latin for, of course, fire. Aris is air. Aqua is water. And terra is land, or earth. So those are the four elements here. And, you can see, and these people have sickles and swords and stuff like that. This very, with the astrological disk right behind it. So you can see that there's a strong correlation between the metaphysical world and the earth, air, fire, and water concept that was carried over well into the Christian era, probably into the mid 1400s in some places. Um, Finally, it was in the 1800s, meteorologists and a school teacher named John Dalton started making some observations that kind of led to the demise of the earth, air, fire, water hypothesis and gave rise to the atomic model. One of these people that started really looking at the atomic hypothesis was a guy named Robert Brown. And Robert Brown is fantastically important in mathematics. But he was a botanist. And let's go ahead and read the blurb here. In 1827, Robert Brown, a botanist, that's somebody who studies plants, observed collisions between visible particles and invisible particles, something called Brownian motion. We'll describe what that is here in this diagram down here. Later confirmed by Einstein as evidence for the existence of atoms. So if anybody's ever on a sunny day been in their front yard or been out on the porch or even in their living room, they see a single beam of light shine into the house, they might notice that little tiny pieces of dust are floating around in what appears to be random order in the air. Nothing seems to be pushing it around. There's no air current, but for some reason it continues to kind of dance around. And what Robert Brown hypothesized was these things are bouncing around not because there's nothing that they're running into. What he was saying is that there must be something they're running into, and those things that are running into it are making it move and dance around. So let's come to this diagram over here to kind of explain what that means. Notice that there are blue dots and red dots on this diagram. The blue dots are invisible. You know, we can see them because we're using a diagram, but imagine that they're invisible and that you can only see them using red dots, right? The only ones that you could see are the red dots. If all you could see were the red dots, you would see these weird particles dancing around all over the place, sometimes speeding up, sometimes slowing down, in complete random distribution. But they would change direction in the middle of nowhere, change speed in the middle of nowhere, and if we had special eyeglasses and we were able to see those blue dots, for example, those dust particles, bouncing into them, the air particles, we would be able to understand why it is that the red dots were moving around the way they were. This is the same thing that Robert Brown was observing in his petri dishes, and the same thing that you're actually observing when you see those dust particles. What's making the dust particles move around and change directions in your front living room on that nice, lazy Sunday morning is the fact that it's hitting atoms in the air. The atoms in the air have energy, and they bounce off of things, and they bounce things around, and ultimately you get what we call Brownian motion, which is this random movement that almost like there's invisible collisions going on that slow things down, speed them up, change directions, the whole gamut. And so that's what this is trying to demonstrate, is Brownian motion. Imagine the blue dots are invisible, and you try to follow a red dot for a while, and you'll start to realize pretty rapidly that that's pretty random. So the characteristics of an atom are pretty straightforward, but there is some really cool aspects to it, just to kind of get right out front. First off, we know that they're incredibly tiny. They're so small. I mean, you can't comprehend how small they are. Some of the features of them, though, are mind-blowing. Okay, they're numerous. I can't even begin to tell you how numerous there are. There are more atoms in a spoonful of sand than there are grains of sand on all the beaches in all the world, by far. There's so many atoms. Okay. Another thing about atoms is they're perpetually in motion. Now, this does not mean they're flowing around like in a river. Typically, atoms are vibrating. You know, even in a solid, say the table that you're eating your breakfast off of, or even the computer you're viewing this program from, is full of atoms, and they're just sitting there vibrating. Okay. And the other thing is they're basically ageless. The material that is in your atoms, in everything around us, those atoms, what we'll find out to be protons and neutrons and electrons, have basically been around since the beginning of the universe, which occurred about 13.7 billion years ago. Before that, who knows what happened to them? So as far as we can tell, they're ageless. That makes them already incredibly fascinating, right? The Earth might be 4.55 billion years old, but the atoms that are within it are actually much older. Absolutely fantastic. And don't worry about this. This is just to demonstrate how big the nucleus is relative to the outer shell. I just thought it was a cool photo, and I put it in there for artistic reasons. All right. So we have some atomic imagery. We do have some idea of what atoms look like to a certain extent. Now we can't use visible light. Why? Because they're simply too small to be seen with visible light. If you use a visible light stream and try to hit an atom with it, there's a major effect that starts to play out. And we're not going to get into the details of it. But there are other ways that we can get images of atoms, and that is that we can manipulate the electron clouds around them. We're going to talk about what the electron cloud is coming up. But we can get a really good idea of what they look like and how they distribute themselves in a substance. And so one of the first images is this one here. This was published in 1970. And these are atoms of an element called thorium. Thorium is a really big atom, so this makes it a very nice target. Here you can see each one of these little spots is a thorium atom. Now, we can't really see a whole lot of detail, but keep in mind, this is still a big deal to see an individual atom in an image, right? Absolutely cool stuff. So revealed as ripples and rings by scanning tunneling microscopes in the mid-1980s. So we started getting better ideas of what they look like. And of course, the classical model has a nucleus at the center surrounded by electrons. So here's what we tend to think of as an atom. This is the atom that we're familiar with since we were in, I don't know, third grade or whatever it is. First time I ever heard about them, or in detail, I never saw a picture of them. And so here would be the nucleus right here in the middle, and around them, orbiting, is usually how we draw it. It's not exactly orbiting, but you get the idea. These electrons. By the end of the course, or today's course, you'll understand the true nature of this spinning electron around the outside. All right, so you'll remember from the previous slide that there were two parts of the atom, right? There's the inner part where the nucleus was, and then there's the outer part where the electrons are. So let's talk about the nuclear structure, which is the middle of it, okay? So the atomic structure is composed of an atomic nucleus, and the concentration of nearly all the mass is right there at the nucleus. By comparison, the electrons are pretty much weightless, so they're massless. And so we usually don't take them into consideration when we're weighing atoms. Almost all the mass is right there in the middle. And there are two particles that are in the nucleus, and they're called nucleons. And they're building blocks of the nucleus. All are exactly identical, and there are two kinds. In a neutral state, it's called a neutron. And so usually we write a neutron as a 0 in the middle of our particle, meaning neutral, right? Because 0 is neither 1 nor -1. It's right in the middle. And the other one is a positive charged state particle called a proton. We usually put a plus on there. Positive charges is an important thing to keep in mind. Positive charges repel positive charges and attract negative charges, right? Basically, anything that is positive is going to repel something that's positive. Anything that's negative, it's going to try to pull towards it. Okay, and it turns out nucleons are further made up of particles in their own right, called quarks. And as opposed to being able to divide a proton directly in half, which you can't do, it turns out that you can break it up into 3 subatomic particles. So a quark is a particle that makes up a nucleon. It turns out there's 3 quarks per nucleon. And they get these weird names. This is an image off of the Wikipedia site of a diagram of the way quarks would be inside, in this case, of a proton. What they call an up quark and a down quark, and their charges are what wind up resulting in forming a proton. We're not going to care too much about that, but it's interesting to know that you can take these things even further than protons and neutrons and potentially even electrons. You can continue going further down, but then no longer do they begin to act like protons. They begin to act like other things. So this is completely compliant with Democritus's hypothesis of an atomic model for matter. All right, so now let's talk about the electrons and the electron cloud. This is actually where it really gets interesting, because the nucleus doesn't do a whole lot. The real motion, the real excitement, actually occurs in what we call the electron cloud. So electrons in the electron cloud. So here's electrons. They're 1/2000th the mass of a proton and are considered almost massless, right? They aren't in fact massless, but they're almost so. and they reside in orbitals that orbit the nucleus. So let's come over to this image over here. You'll notice that this is sodium, Na stands for sodium. So here's the sodium nucleus, and around it are these electrons. Now you'll notice that there's two right here in the middle that are kind of close. I'm trying to track that one right there. Okay, so that's an inner orbital. Notice that there's 8 of them all over here that are orbiting right here in the middle. That's a second orbital. And then there's one on its own out here in a third orbital. It's all by itself. Now this is an important one to keep in mind, this guy here. We'll kind of come back to him soon. Okay, so all electrons are identical in a negatively charged state, equal to but opposite to protons. So even though they're 1/2000th the mass of a proton, they have the exact same charge, except it's negative. This is really interesting because this fulfills Newton's third law that for every force there's an equal and opposite force coming back the opposite direction. So this is completely compliant with Newtonian physics. Anyway, so we should keep in mind now that there's structure to the electron cloud. We've kind of brought this up. You'll see that these things are spinning around. Notice they're not even spinning at the same velocity. The ones in the middle are going faster than the one way out here on the outside. So they have very different physical parameters that we need to keep in mind. Now, electrons whirl around the nucleus in a cloud of motion at 2.2 million meters per second, which is 1,360 miles per second. And I should actually clarify this and say it's the electrons here closest to the nucleus are the ones that are going that fast. The ones on the outside go a little bit slower. This is about 1/130th the speed of light. It's still very, very, very fast, but it's not anywhere close to light speed or anything like that. So how fast is 1,360 miles per second? It's fast. Let's just say that a single atom of, when I did this calculation, was for helium. A single helium atom, the hydrogen that goes around it, just one of them orbiting the nucleus, it could actually go around the Earth approximately every 20 seconds. That's a lot. So imagine all of the little atoms in you, and the electrons are sitting there spinning at such a high speed that they're putting on, that they could actually, each one of them could orbit the Earth every 20 seconds. That's amazing. That's amazing that electron clouds have that much activity going on in them. That's such high speed. Okay? The cloud is actually structured into energy-controlled orbital shells, and this is what we were implying when we were talking about this here, right? The inner, the middle, and the outer for the sodium, that these are actually shells of electron distribution. And they don't actually follow this. This is what we would call schematic operations. It turns out that they actually move in a figure-8 pattern. But this is good enough for our discussion here. And the outermost electron shell houses the valence electrons. This word valence means outside or outermost. And so here's our valence electron here, the one way out here on the outside. Okay, so this would be the valence electron, or the valence electron shell right here on the outside, of which there's one electron. Okay, valence electrons are the most weakly held by the nucleus, and they tend to be easily lost by the atom, causing charge imbalances. So you can imagine this little guy out here can be plucked up by another atom that happens to be looking for an electron for whatever reason. And if it does so, that's going to create a charge imbalance. Sodium wants to have all of its electrons, but if it loses it, it means you're going to have a charge imbalance, which makes the atom have itself a charge. All right, so let's talk about what the elements are then. Okay, first off, the elements refer to particles that make up a substance, which is to say the atoms in the elements. And an elemental substance is composed of only one kind of atom. So this is really kind of cool. The lightest and most abundant is hydrogen. And to date, about 115 are known. Now some of these are made in laboratories, about 25 of them. But 90 are known to occur in nature, including uranium, hydrogen, thorium, you name it. Others produced in laboratory are unstable, which is to say radioactive. And the words atom and element can be used interchangeably. Usually we use the word atom to mean a specific small part of an element being a pure form of something. So here we see a big chunk of, or this is actually the element mercury, which is a liquid metal being poured into a Petri dish. And this is a lump of what I think this is actually a lump of platinum, if I can remember. Platinum is also an element. So what is the purpose of the periodic table of the elements then? Well, we've been hearing about it since we were kids. We've seen them up on chemistry walls in every science room. It's kind of an icon. But do we know what this means? Sure, at this point we could actually start explaining it pretty easily. First off, a periodic table is simply a chart, but it's really better to call it a map. It's really not a chart. It's only a chart in so much that it hangs up on a laboratory wall. It's really a map of elements arranged by the number of protons in the nucleus, which is the atomic number. So if we look over here, here's an atom being drawn, and we can count the number of protons. 1, 2, 3. 3 protons, 3 electrons. That's interesting. So that must mean that this element, whatever this is, would have an atomic number of 3. So arranged from left to right, each having one more proton and electron than the preceding element. So we'll look at the periodic table on the next slide. But when we look at this thing, we said that this thing would have 3 protons, atomic number 3. Oh, look, there it is, atomic number 3. Lithium is the name of that atom, that element. And of course, on the far right, outer shells are filled to capacity, known as noble gases. Let's look to see what this is talking about here. Each one having more than one proton, electron of the preceding element. All right, let's see if that makes sense. All right. So yeah, this is exactly what it's saying, right? Here's a hydrogen. Hydrogen's got an atomic number of 1. So it has 1 proton. Let's go to the right. Here's helium, element number 2. It's got 2 protons. It's therefore got to have 2 electrons that go with it. What's the next one? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, right? You get the point. Each one of these elements is based upon the number of protons. So if I want to know how many protons are in gold, gold is right here. Well, gold is the atomic number 79. It just means it's an atom with 79 protons. Very, very easy. There's another thing we should kind of keep in mind, which is the atomic weight. Also, it's frequently also called the mass number. You'll hear both. They're used interchangeably. Those of you that wind up taking more advanced chemistry will see that there's subtle differences between the two, but for all intents and purposes, at this point in your career, they're the same thing. So to understand the atomic weight means that we have to learn about something called isotopes. So let's look at what the atomic weight is. So the atomic weight is the average sum of the nucleons in an element. Remember what a nucleon was, right? A nucleon is a proton or a neutron. So for example, hydrogen has on average an atomic weight of 1.008. But notice that's not exactly 1, right? Hydrogen has 1 proton. So why is it showing a slightly larger number than 1 nucleon per average hydrogen? Well, it means one thing. It means something pretty profound, actually. It means that hydrogen atoms occasionally contain more than 1 nucleon. And this is called an isotope when this happens. So an isotope is simply atoms of the same element with different numbers of neutrons. And they have identical chemical behavior. Let's go back to hydrogen. Hydrogen, turns out, has 3 isotopes. Iso meaning same, tope meaning type, same types. So hydrogen, hydrogen, hydrogen. How do we know they're all hydrogen? They each have 1 proton. 1 proton, each of these, right? It's all in the atomic number. Atomic number is 1. Okay. Symbol for hydrogen, of course, is H. All right, so let's drop back down this diagram. What's the difference between these? Well, there's this regular single proton hydrogen with no neutrons, but all of a sudden now we have one called deuterium. Deuterium, it turns out, has a neutron. It has 2 nucleons in it. Deuterium, meaning terium, meaning elements. Tritium, same thing. 1, 2, 3, 3 is actually the number of nucleons in the nucleus, and we have tritium there. But they're all hydrogen. The difference between them is simply the atomic weight. It does turn out, just as a side note, that tritium is so heavy and so unstable that it actually is a radioactive form of hydrogen, whereas this one and this one, deuterium and hydrogen, are completely stable and fine. So we also need to bring up this concept of an ion. I started leading into that a little earlier, and I had to detract away from it. Let's come back to that. So an ion is a charged atom. Right? Remember, we were showing that sodium earlier, and I said if it loses that outside valence electron, it's going to get charged. Well, that's what this is. It's going to be charged and be called an ion. So a positive ion has a deficiency of electrons, sometimes called a cation. So if that sodium was to lose its electron, way back in that earlier slide, I'm going to slide back there. So if this sodium loses this valence electron, it means that there's going to be more protons than there are electrons. So sodium is going to get a positive charge, and that's going to turn it into a cation. Now, if it steals new electrons, then it would get a negative charge, and it would basically become a negative ion, and that would be called an anion. Right, meaning having a stronger charge. So here's a diagram of it. You have a neutral atom. It gains an electron, it becomes an anion. If it loses an electron, it becomes a cation. And so it turns out that the relationship of these cations and these anions have a dramatic effect on the size of the atom itself as it sits in space. Right, the nucleus is this little thing, but the electron that's moving around the outside can orbit at very large distances or very small distances relative to the size of the nucleus. And so that has a dramatic effect on the size of the atom. So here's something you might not have predicted. Here's hydrogen, and here, right here, this little circle, okay, that's the size of the hydrogen atom. Let's go over here. You would expect helium, which has twice the atomic weight. It actually has 4 times the atomic weight, but twice the atomic number. It should be bigger, but it's actually smaller. And the reason why is because it has a very good charge balance. It has 2 protons, and those 2 protons are able to pull those electrons much more effectively than the single proton in the hydrogen. And it turns out it makes the heliums smaller. Same thing is true down here. Look at how big this potassium ion is, right? It has fewer protons, but it's larger than the krypton, which is way over here, which has a lot more protons and therefore has a stronger pull on its electron shells. So it pulls everything in. So interestingly enough, the cations, which are these guys over here generally, are large. The anions are these things over here. They tend to be small. As nuclear charge increases and electrons are added to outer orbits, the inner orbit shrinks. It makes perfect sense, basically what I just said, in different words. So now we've been talking about atoms and their structure and their charges and their size, and we haven't really gotten into how they might interact with one another too much. This is really the most important part of the whole lecture. We said that other stuff to say this part right here. And in order to understand everything else going on in the chemistry of the world, we have to understand molecules, compounds, and mixtures. So what is going on here? When 2 or more atoms bond to one another, they make a molecule. Okay, so 2 atoms coming together for whatever reason, they bond. We're going to describe these bonds here shortly. A substance made up of molecules is called a compound, right? A substance made out of all atoms is called an element. As long as there's no molecules in there, it's all an element. But in this case, this is the equivalent. Anything that's made up of molecules is a compound. A compound behaves chemically different from the elements from which it is made. I hope so. Hydrogen and oxygen behave very differently than water does, which has both of these. This is the water molecule right here. Can only be separated into its constituent elements by chemical means. It would require an actual chemical experiment to be able to separate these items one away from each other. And the reason why is because it takes energy to make this reaction happen. So an example of this would be, for example, table salt. Table salt is a compound of sodium and chlorine, sodium chloride. Sodium is a poison, or actually sodium is an explosive poison, and chlorine gas has actually been used in execution chambers. Put them together, you can make table salt. It's absolutely incredible that you can do that, but it's true. A substance that is composed of elements and compounds mixed together without chemically bonding is called a mixture. An example of this is air in our atmosphere. We have argon and oxygen and hydrogen and helium and carbon dioxide and xenon and argon, but they don't form any large molecules except on occasion. Carbon dioxide forms a molecule of carbon and oxygen. But that in and of itself doesn't form anything with argon. So they're a mixture. They coexist without bonding to one another. Okay? So what kind of bonding occurs between elements? Well, it turns out there's three main types. There's the ionic, the covalent, and the metallic. We'll come to covalent here in a minute. This is probably the most important for you to remember. But the ionic bonds are basically attracted via charge. So in this case, we have sodium and fluorine. Now watch what happens here. The valence electron on the sodium is transferred to the fluorine. The fluorine actually is going to go ahead and steal it. What does that do? That turns the sodium into a positive charge. We'll watch it again. It'll turn the sodium into a positive charge and the fluorine into a negative charge, and that will attract them one to another. That is what we call an ionic charge, right? The fluorine has just stolen the electron outright, and in doing so has created a charge imbalance, and now they're attracted through the charge imbalance. By comparison, we have covalent bonds. So here we have a hydrogen, which has one electron unto itself. And then we have, in this case, two hydrogens. But notice that they can bond one with another. This one has its own electron, this one has its own electron, and they're able to actually share the two electrons equally rather than each having their own. And this has a very important thermodynamic value. Hydrogen by itself does not actually like to just simply be alone, what they call basically a proton with an electron in space. Hydrogen and many other elements like to share their outer shells as much as possible. That way they don't have other elements stealing them as easily, and for lots of other reasons as well. So in effect, they bond with one another to get this mutual benefit, and it's called covalence, right? Co meaning shared, and valent meaning outside. So they share these electrons, these outer shells, one with another. And the third one are the metallic bonds. Metallic bonds are basically the free movement of valence electrons. So these atoms are in here, say they're basically metals of some sort, and they have positive charges, perhaps it's iron or something like this. And this electron here has the ability to just kind of skirt around throughout the lattice of these, lattice meaning the structure or the distribution of atoms, can move throughout the lattice of atoms freely, as long as it's on the outer part of the atom. So the valence electrons can move freely. This is actually what makes metallic substances good conductors of electricity as well as good conductors of heat. All right, let's do a quick overview of chemical reactions then. Okay, so a chemical reaction is simply a process in which atoms rearrange to form different molecules, usually for their mutual benefit, right? They want to fill up that outer shell, or there's a charge imbalance, right? An example would be pulling molecules apart requires energy. So during photosynthesis, sunlight's energy breaks bonds of carbon dioxide to produce O2, which is oxygen, and carbon. Combining atoms releases energy. So oxygen atoms combine with iron atoms to form rust. And it turns out basically what you're doing is releasing heat in the same time that you are doing that transaction. So the release of energy is actually what nature normally does. But during photosynthesis, it's taking in energy from the sun. So it's putting energy in. So this is two ways that rearranging of molecules or rearranging of elements deals with energy issues. So here's, for example, the burning of methane. Methane is CH4. So you take that, you burn it in the presence of oxygen, and it forms carbon dioxide and water. So I just decided to go ahead and throw this in here. This is really cool stuff. In addition to regular matter, there's the flip side of it, and it's called antimatter. It's basically where you just take all the charges of the subatomic particles and reverse them, right? So matter is composed of atoms with positive nuclei and negative electrons. What is antimatter then? Antimatter is composed of atoms with negative nuclei, which are made up of antiprotons and antineutrons, and positive electrons, and these are called positrons. Here's a antimatter atom as it would exist, where you have an antiproton in the middle and a positron on the outside. So positrons have the same mass as an electron but are positively charged. And antiprotons have the same mass as protons but are negatively charged. Both matter and antimatter cannot exist in our environment. As a matter of fact, whenever we have created a positron, it has annihilated itself by combining with a piece of regular matter, usually an electron, and basically turning itself into pure energy. Pretty cool stuff. They have, in fact, made, very briefly, a antimatter atom I believe, in a super collider. My memory is good on this. Absolutely incredible stuff. In addition to that, it's kind of neat to know something about the stuff called dark matter, right? So we've got all matter. We've been talking about these compounds, antimatter. Dark matter is something that is a totally different nature. So what is dark matter? Well, dark matter is unseen and unidentified matter that is very different from the elements that comprises about 23% of the matter in the universe. Okay? That's a large amount of material that we know nothing about. What about if you're going to have matter, you probably also have energy that's dark, right? Yeah, it turns out dark energy is an anti-gravity energy composing 73% of the universe. Wow. We don't know almost anything about it. That means that what we know about the universe is still very nil. How do we know about all this stuff? We're going to show you an image that kind of demonstrates why we believe that dark matter exists and how we can take these measurements. So finding the nature of dark matter and the nature of energy, which is to say the dark energy, of empty space are high priority quests in these times. There's all kinds of physicists and astrophysicists working on this very question. What we will have learned by 2050 will likely dwarf all that we have ever known. And yes, knowledge in this subject is just piling on top of new knowledge very rapidly. And at some point, some very smart people are going to get together and figure it out. Hopefully within our lifetime, because I'd like to really know what this stuff is, what dark matter is, and what dark energy is, and how it relates to us. So what is this image here? This image here is a piece of dark matter, basically a black hole. This is kind of the ultimate form of dark matter, right? Because we can't see it as it goes through an illuminated cloud of gas. And notice that as it goes through, it actually bends the light waves around it, almost like the way that a lens does. As a matter of fact, this is called lensing. And it implies that there's a big gravitational force in the middle. So here's that lensing effect. This is actually taken by the Hubble Space Telescope. And you'll notice that all of these things form nice circles. See how this is forming a circle? This is almost like looking into a giant lens. And so how do you get this? It means that somewhere in the middle of this image, right about here, is a very, very, very heavy object, a very massive object that has the ability to actually bend space by its mass. And in doing so, it implies the existence of dark matter. And of course, when we look into the image, we don't actually see what it is, but we can see the lensing effect, just as we had seen on that image of a simulated black hole going through a illuminated cloud of gas in deep space. Let's go back again. Cool. So I hope that you enjoyed this little primer on atoms and matter and chemistry and the effect of dark matter on our solar system and on our universe. If you have any questions about it, feel free to give me a quick email. Until next time, bye.